Even and odd functions, problem type 2. While it's nice to be able to look at the graph of a function in order to determine whether it's even or odd, if we don't have the graph, we should still be able to do so. And an analytic approach is going to give us a more reliable result than trying to make a judgment call, especially if something is nearly even or nearly odd. But in our case of mirror symmetry, the even function, we want to get the same y value out whether the x coordinate is positive or negative. So to set that up, we'll say that f of x is the same thing as f of the opposite of x, right? The y coordinate of the function is the same whether you use a positive or negative value for x. For an odd function with rotational symmetry, we looked at switching both, right? When you visualize rotating this thing around, your positive value for x becomes negative, and your positive value for y also becomes negative. So in an odd function, we're looking at f of the opposite of x should be the opposite of f of x. That gives us the test we need. If we take a function and plug in opposite of x, we'll see what we get out. If we get out what we started with, then we have an even function. If we get out mostly what we started with, but everything is negative, then we have an odd function. If we get out something else, then we have a function which is neither even nor odd. So let's take a look at a couple of examples. F of x is x to the fourth plus 2x squared. To test this for symmetry, we're going to evaluate at the opposite of x, which means we have the opposite of x to the fourth power plus 2 times the opposite of x squared. And using the multiplicative property of exponents, this is negative 1 to the fourth times x to the fourth plus 2 times negative 1 squared times x squared. Negative 1 to the fourth is 1. Negative 1 squared is 1. So we end up with x to the fourth plus 2x squared, which is exactly the function we started off with. So we can conclude that this is an even function. If we have g of x, which is x cubed minus 3x to the fifth, we can test this the same way. Evaluate g at the opposite of x, which means we want the opposite of x cubed minus 3 times the opposite of x to the fifth power. Once again, we can use the properties of exponents. This is negative 1 cubed times x cubed, and negative 1 to the fifth times x to the fifth. Negative 1 cubed is negative 1. Negative 1 to the fifth is also negative 1. Multiply that times negative 3 is going to give us plus 3 x to the fifth. And we can see here that term by term, the sign changed from where we started to where we ended up. So I can factor out a -1, leaving me with x cubed minus 3x to the fifth. So this is the opposite of g of x, which is exactly the conclusion we said we needed to come to have an odd function. One more, h of x is x cubed minus 1. If I try to evaluate h at the opposite of x, I'll get the opposite of x cubed minus 1, which is -1 cubed times x cubed minus 1. -1 cubed is -1, so we have the opposite of x cubed minus 1. We have the same terms. We have a negative in front, but if we try to factor out the negative in this case, we would end up with x cubed plus 1. So this is not h of x, and this is not the opposite of h of x. This function is neither even nor odd.